Today we're going to be talking about EM, which is the expectation maximization algorithm. Last class, Dr. Lehman gave us a really good foundation in what mixture models are, and he started to prelude to what this algorithm was. Today we're going to take a more general approach to it and try to answer these three questions. What is the goal of EM? How does the algorithm that Dr. Lehman briefly mentioned achieve this? And then can we convince ourselves that the goal and the algorithm are aligning? Now, I came up with these three questions because when I was first learning it, these were the three questions that helped me develop my understanding. And so the whole idea of what we want to do with EM is we want to infer parameters given data. So our goal to infer parameter, which we'll denote as theta, given data, which we will denote as D. We're keeping it general. We won't be talking very specific mixtures. That's going to be next class. Okay? So our idea is to do this, and what makes EM so special is that it allows us to make inferences about theta, our parameter, when we have missing data. And so we're going to let psi represent our missing data. Missing can also mean latent. So we have two problems. We have the Cassel-Berger problem, which talks about the multiple Poisson rates, and they are talking about missing an actual data point x1. And so they would be treating psi as x1. For our mixture problem, it's the labels. What are those class labels? But we're going to keep it general. And so our model is going to be f of psi theta conditioned on our data. This is what we see. We have our latent, we have our parameters, and we have our data, which is observed. And this pen is dying on me.
Can you hear me?
Yes.
Would you mind moving the laptop a bit closer?
Absolutely. Is that better, Daniel?
Yeah, that's good, thank you.
Awesome. No, thanks for letting us know. Okay. So our goal is to infer theta. And this is the goal of the expectation maximization. But how we do it is through... Oh man, these pens. Theta, we're going to argmax. So, in a normal problem, if we were trying to figure this out, we would average over our latent variables are missing, and then we would want to max over the theta. This theta hat represents our best guess at theta. So all EM is doing, and the goal is to get rid of our missing parameters through averaging, and then we just want to maximize over to find our best value of theta. We can also write this. This is going to be for a little bit also write this as arg maxing theta. We can call this chunk right here capital F of theta d. This is the marginal. So we're marginalizing or averaging out our psi parameter. So the goal is to find this theta, best guess at it for our step. Now, that's the answer to question 1. The second question, which Dr. Lehman talked about last time, was the EM algorithm. So let's take a look at the algorithm real quick and how it achieves. Okay, the EM algorithm takes 2 steps and a sub-step. Sub-step is you need to initialize your thetas at some value. Okay? You're going to have to do that. Then, for t to big T, we want to take the first step is going to be the E step, and the second is going to be the M. First, we got to take an expectation. What that expectation is the expectation of the log. Okay, all right, what's this? Of our f of now, what are we taking the expectation with respect to? It is respect to psi conditioned on the previous, I'll make that bigger next time, previous parameter. Okay? Once we take this expectation, which let's take another step, because this is simply looking at the integral log times, I'm going to make sure I get my notation right. Yeah. Okay? This will come to play when we start trying to do the proof of showing you guys why this works. The maximum part is just saying theta hat of our next one is the arg max theta of this. And there's 2 things though that questions, and which we'll talk a little bit more about next class when we're implementing the algorithm, is what is this t? This t is going to be for some large number, because it's an iterative process, or you can, instead of doing a for loop, you can do a while loop, and there's a convergence criterion. Let's save that for next class when we're actually looking at the algorithm itself. So the next question, and this is where we're going to spend most of our time, is how can we convince ourselves that this iterative process is equivalent to doing this step? Let me repeat that again, because the proof is that can we prove to ourselves taking these 2 steps iteratively will get us this? And this is what we're going to spend the remainder of the class talking about. And so the first step to figuring this out is trying to, with any proof, is trying to understand where we have to start and get there. And what we're going to do is we're going to start with Bayes' theorem. And I know a lot of you guys should remember this, but it's always a good thing to remember. In general, when we typically look at this, we'll have some f of x, keeping it general real quick, y, conditioned on some y, I feel like I'm messing something up. Yeah, because I am. Okay, typically in your probability first class, you'd see something like this. The thing that confused me when I first was doing this was that there was no data statements and how it looked. So I'm going to generalize this to our problem, and we will have, let me get my notation right. We have something like this, where this is the conditional distribution of psi given our theta and our data. Here is our joint. Here's our marginal. Okay? Now, I of course erased the goal, but that's okay. When we were looking at our goal of EM, we had this in there. Because our goal, I'll rewrite it because I think it's very important. We had this. And so we have this. So all we're going to do is we're going to do a little bit of rearranging, and we're going to get And so this is our first step, is we now have something that matches our goal. Our next step is to see if we can get something that can match this chunk right here. And so what we're going to do is we're going to take a log, and then we're going to take an expectation with respect to psi. The reason we can take a log and preserve our maximum is because f is being treated as a posterior likelihood or some positive function. And so we get, I'm going to do two steps at once, and I'm going to run out of space potentially. Minus now don't forget, all this is to the respect of psi given the previous step. Okay? The thing is, I'm going to erase this chunk, I want to keep that up there. Is we're going to notice two things. This part right here, when we take the expectation with respect to psi, there's no psi's in here. So that will simply,
excuse me again.
yes.
Would you mind turning the camera slightly?
That way?
Yeah, that's good, thank you.
No problem. So there's no size in here, so taking the expectation is something that doesn't have the random variable in there, is treating it like a constant, and you drop it here. Then this part is this part. And so we're going to redenote this. Not redenote it. Q. Boom. This part, star, is here. So we have our, apart from our iterative step, and we have apart from what our actual goal of EM is. But we have this extra chunk right here, this minus, I'll call it triangle, minus the expectation of the log of the conditional. For simplicity, we're going to call this S, theta, addition on theta. Okay? Now, from looking at this, if we maximize over this equation with respect to theta, we would have our goal, we would have the E step, but we'd have maximizing the step, so we'd have this, but we would also have this extra part right here. And so when we take the maximization, these two aren't exactly the same. But what I'm going to show you is that this S is decreasing when we increase this Q. Okay? And what that's going to show us is that if we iterate through this, we will converge, we will limit to what we really want to show. Alright? So let's get started on trying to prove that this S of theta as Q of theta, theta t minus 1 increases. We're going to start with a fact, and from that fact, we're going to break down and get to the good parts. So fact. The log integral of f psi conditioned on theta t d psi is equal to 0. Yes, I do mean to put a t there. We'll get to that in 1 second. And the reason why this is true is because this function right here is integrating over the entire space. So we have a probability measure and we're integrating over the entire space. So that's 1. The log of 1 is 0. Alright? From here, we're going to multiply by a fancy 1 we're going to go f of psi conditioned on theta t minus 1 times f of psi conditioned on t minus 1 d psi integral. So all we did from here to here is we multiplied by a fancy 1. Now we're going to use the definition of expectation to get equals 0. The expectation respect to psi theta minus 1 is f psi Now we're going to use a property that is called the Jensen's inequality. And for you guys, as a reminder, Jensen's inequality states for concave functions, which we're working with the log, that if we have some function g, which is containing an expectation that will be greater than or equal to expectation for convex it's the other way around. How do you remember those? Concave looks like a cave, convex doesn't look like a cave. So we're going to apply Jensen's inequality here, and we are going to get the log f So all we did was apply Jensen's inequality. From here, we're going to do a little bit of algebra, which is expanding this out and pretty much doing the reverse of the expectation definition that we used here. And we're going to see something pretty cool. Of f psi conditioned on t minus minus the expectation, the log of f psi conditioned on t. What we're going to see now is if we expand this one more time, being a little bit superfluous here, you guys, integral of the log of f psi conditioned on t times f, remember what we're d psi. Sorry about that one. What we can see here is, erase the s function. Is that this right here, this chunk, will represent s of theta t minus 1 minus, and then this right here will represent s of theta t minus 1 conditioned on t minus 1. And what we can see is that if we move this over, that our next step, t, will always be smaller than our previous t minus 1 step. And so what we just showed is that the s function is decreasing. So a little visual of that would be is if we have s of our theta, here's our theta t minus 1, the step we're at, it's going to be decreasing away from it. That is important so that as we are getting closer, the function that we saw previously what is this? This is getting smaller while this is getting bigger. So if we keep iterating over it, we will limit to our goal. So going over the 2 EM steps will limit to our goal of finding an estimate of theta. So I know I've said a lot and it's been a little messy, but we're going to take it one step real quick and try to recap everything. The goal of EM is to find this. What is this representing again? Marginalizing over the size and then taking expectation. How is EM actually doing that? It's going through an iterative process of taking an expectation of the log of the then it's maximizing over it. What we showed through proving that this S function is decreasing is that by going through these steps iteratively, you will get here. Now, the question is, this right here, when Q is closed, is simple. And what we're going to show next time is that for our mixture models and even for the Poisson problem in the book, we can find close form solutions and we can just iterate over those. And it's simple, but it requires a little bit of math. And the math that in order to start with, and I'm going to leave as a question for you guys to think about, is what is the likelihood function for a mixture model? Because we're going to need it right here, and then take the logs, take the expectation. But if we can't derive the correct likelihood, we're going to be stuck there. So I just want you guys to think about this over the weekend. Try to derive it yourself. I know when this is an in-class session, Dr. Lehman always tries to bring someone up to the board, and we kind of talk about some of the problems that happen. So next time I'm going to talk about how some of the common mistakes and why we make them, go through some of the derivation, and then show some examples. So until then, we will go to Zoom. Dr. Lehman, do you have any comments you'd like to add? Nope. So see you guys, and we'll go to Zoom. Bye.